In today's world, a significant portion of the energy consumed in buildings is dedicated to heating and cooling systems. According to international statistics, approximately 40 to 50% of total energy consumption in the residential and commercial sectors is related to air conditioning, heating, and cooling of interior spaces. This not only increases energy costs for consumers but also places additional pressure on energy distribution networks in densely populated cities and regions. Moreover, it contributes to environmental pollution caused by the combustion of fossil fuels such as natural gas, diesel, and fuel oil. Additionally, the emission of greenhouse gases such as carbon dioxide and methane, direct results of excessive energy consumption in the building sector, accelerates global warming and climate change. On the other hand, severe temperature fluctuations during the day and seasonal weather changes create significant challenges for energy management. In particular, during spring and autumn, when weather conditions are more unstable, manually controlling the indoor temperature becomes very difficult, leading to increased reliance on heating and cooling systems. One of the major problems in many traditional buildings is the inability of common construction materials to respond to these temperature fluctuations and to maintain thermal comfort in an automatic and optimal way. The fundamental issue with many conventional construction materials such as ordinary bricks, cement blocks, and non-advanced concrete is that they lack dynamic thermophysical properties and cannot adequately react to temperature variations. In other words, these materials are neither capable of absorbing heat during the day, nor storing it within their internal structure, nor releasing it in a controlled manner at night or when needed. As a result, in cold seasons, the heat absorbed during the day is quickly lost, and the interior space requires more artificial heating. Similarly, in hot seasons, these materials are unable to prevent external heat from entering the building, which significantly increases indoor temperatures and necessitates the use of high-consumption cooling systems such as air conditioners. In response to this critical need, the primary goal of this invention is to design and produce an advanced type of building brick with intelligent and self-sustaining temperature regulation capabilities. These bricks utilize phase change materials, PCM, which possess high thermal capacity and can undergo phase changes, from solid to liquid and vice versa, at specific temperatures, absorbing or releasing a substantial amount of thermal energy, without experiencing significant temperature change themselves. The mechanism of these bricks operates as follows. During the day and under sunlight exposure, excess environmental heat is absorbed, causing the PCM inside the brick to melt. In this process, thermal energy is stored in the material in a latent form, preventing it from being transferred to the building's interior. At night, when the ambient temperature drops, the PCM ray solidifies, and during this phase change, the stored heat is gradually released. This feature helps maintain the interior temperature of the building within a balanced and comfortable range, reducing the need for constant operation of heating and cooling systems.